MD. He received his MS degree in applied mathematics from Pierre at Mary University and a PhD from Sorbonne University and INRIA Paris. He's a research associate at the Innovative Computing Lab, ICL, at the University of Tennessee, Knoxville. He worked on the FFT library, of the FFT computation, on the exascale systems, and the FFT benchmarking software initiative. Now he has moved to AMD, and so he will be talking about scaling communication for large-scale FFT on GPU-based supercomputers with modern interconnects. So let's welcome Alan.
Thank you for the introduction. Today I'm going to talk about fast Fourier transform. As you have seen during this conference, many people have talked about FFTs, and another subject has been, for instance, the all-to-all communication. So in many of these talks that we have been having here, they mentioned FFTs, they mentioned all-to-all. I'm kind of going to put this in a context for scalability and how the FFT heavily relies on these all-to-all communications, and what is the impact for applications as well. So this is just the outline of my talk. I'm going to introduce first the FFT and what it is being used in modern applications, and then I'm going to review some implementations of the FFT. And an interesting part will be the network topology effect on the scalability of FFTs. And I'm also going to analyze the effective bandwidth that we can achieve in modern supercomputers. And another subject will be the collective operation and MPI distribution, how they impact scalability. And we will see some experiments using large FFTs. So before I move on, I think the most essential part will be the collective operations. And we have been having some fruitful collaboration with the MBI pitch team. Just let me tell you, for instance, I came here, well, I was invited to the 2021 talk where I presented how the mixed precision and compressing communication can help us to further scale FFTs. And Dr. Panda and his team, they created this new feature on MBI pitch, as you saw yesterday on Harry's presentation. So today I hope the details I present here can inspire novel developments on this area as well. First, the FFT, as you may know it, how it's defined, and we can start from directly tensor multiplications. Essentially, that's what the FFT does. It does a product of two tensors, and it's the fast Fourier transform itself is a way to compute a discrete Fourier transform in an accelerated time. It's one of the top 10 algorithms of the 20th century. And their implementation was started on the 60s, 65 by Kulitaki. And essentially what we are trying to do is we have this n-dimensional array, and we want to compute the discrete Fourier transform, which is defined as you can see it here. And this can be done naively, cos n squared at scale, and with the FFT algorithm, we can do it in n log n. So we have other implementations other than the Kulitaki algorithm. For instance, many fast kernels use also the Bluestein algorithm, which has another set of properties. But essentially, this is what we have. We need to compute this product. And the structure of this product help us to provide efficient algorithms for this, even in parallel. So where is the FFT used and why do we need it to scale? The FFT is heavily used in applications. According, for instance, to dimensions.a, just year to date, there is over 82,000 papers mentioning fast Fourier transform. 60,000 of them are in journal or conference papers. So the FFT is heavily used in applications in science and engineering. And as you can see here, there are some very well-known software like LAMPS in the molecular dynamics area, and also HACK in the aerospatial set of codes. They rely heavily on FFTs, and they are increasingly requiring higher or larger size FFTs. For instance, HAC is hoping to use over 20,000 cube grid sizes. They have a paper from last year where they show scalability to 1.5 million MPI ranks, which is pretty hard to achieve. There's many papers that have tried to go to over 1 million processors, and at scale for all-to-all communication, it's very, very hard. And we have also these new sets of applications, the RTM ones that are being highly studied today on GPUs mainly. This is the third part is mainly for GPUs applications that I will comment later on as well. And as you can see here on the right, we have, this is also from a paper from last year. We have an application here where we are seeing that the both implementations of the Poisson kernel that they require, they can take over 50% of total runtime. That depends also in the cutoff that you use. But in general, you can see something like that in many applications. And that's why it's very important to accelerate this in parallel. So concerning the state of the art, I will mention some of the libraries that have been developed. One of them is started like more than a decade ago to decompose, and it's currently now it restarted development, and they have added CUDA-aware support. They have also been adding AMD support for the library, and they are showing a pretty good performance. This is a Fortran code. ACC FFT library, they currently only provide QFFT, and they stopped development. But they provide very good tools like Laplace and divergence kernels, which are very useful in PDE applications in parallel. The QFFT MP library that was also released a couple of years ago, and this is a vendor implementation, and it relies on libraries like MBHMEM, and they provide a very powerful API for computing many kinds of multidimensional FFTs. One of the oldest library, actually, one of the first libraries that started with support in parallel FFTs at scale with GPUs is DigPath, which is like they intended to move P3D FFT to GPU level, so they just replaced the FFTW backend with QFFT, and they achieved very good results. Still, they imagine that the future, this is a 2010 paper, so they did that back there, and they estimated that when we get to exascale, we're going to get 40% of runtime will go to communication. But nowadays, we know that it can be over 95% of runtime or everything on communication. So here are some of the libraries that are right now being used on current development. FFT library, or the fast Fourier transform in the East, is one of that supports many kinds of decompositions, like the pencil and slab decomposition. But it has some limitations. It doesn't support generic grid dimensional sizes of the processor grids. FFT MPI is a library that is targeting molecular dynamics applications in particular, and it has supports for NVIDIA and AMD GPUs. Hefty library is a library that I worked a lot in the past 5 years, and it also supports, it added support to Intel GPUs as well. And we also did provide these convolutions and sine cosine transforms. This is being used as the XXL project applications. So these two libraries here on the end, MFT library is a very recent one. This was just published like 1 month ago. This is trying to do something very interesting, which is to trade off precision with the amount of volume that you will communicate. This is also in line with what the MBI pitch team did on compressing data and to arbitrary compressions rates. And here, the SPFFT library is also a GPU-based distributed FFTs. And the idea is to support for sparse FFT, which are encountering some kind of applications where they have the data in the frequency domain. So here is one of the points that I would like to discuss here today. We can maybe at some point create an all-to-all routine that can support sparse data already, Because right now, when you have your all-to-all communication, you assume that your data or your buffers are dense. But if you can consider that most of my buffers will be sparse, most of my entries will be zeros, we can do some optimizations. And right now, there is no MPI library that can precisely handle this kind of cases. So it would be good to have some progress in that area. And here is the algorithm. I try to summarize here all possible implementations that are on the state-of-the-art libraries that I show. We have the pencils, slabs, and brick decomposition. So in general, like in the QFFT-MP API, you can provide the general brick decompositions like you have here in the middle, and you can exchange your data patterns between them. And essentially, you have computation of FFTs on the pencil directions here on these three, and the left, right, and the center. And the middle ones will be the communication. That is an all-to-all communication that there are many ways to implement it. There is a paper, for instance, using the whole thing, all the communication process that is needed. It can be moved to all-to-all W, for instance. That was an application that I showed last year on the MAC conference as well. And here, essentially, we need to compute local FFTs, many of them, low-dimensional FFTs, like 1Ds or 2Ds, and then put them in a way contiguously in memory that can accelerate the exchanges, and call a MPI collective or binary communication, and then in the receiving GPU, we do the unpacking. So the FFT algorithm itself, or the FFT computation, is done by high-performing libraries like RockFFT, CoFFT, or Intel MKL FFT. So here, I'm going to present now how this scale and how we can calculate the cost for a machine-based with a bandwidth of W and a latency of L. So we have three approaches, as I was mentioning: the slabs, which are 2D structures. If I put my data in this kind of slabs decomposition, I will have only the need to do one transposition step from one state to the other, as you can see there. So I have 4 communicating units. And then we can easily calculate the number of, or the volume size that I will need, and the number of messages that I will send. And like that, we can estimate the communication total cost based on latency and bandwidth, which will be that number or that expression there for the slabs. For the pencils, we can do the same thing. Now we have a grid of processors, which is bidimensional. We split our grid in both directions. And this is the communication cost that we will have and the number of messages that we need to send. So we can calculate that explicitly. And for the brick decomposition as well, if we have a brick here, we have now 4 steps of transposition, and we can calculate the number of messages and the total volume of communication. So having these formulas, we can see what happens at the scale. Here are for the 3 cases, slab, pencils, and bricks, and how many processors are here intervening for the computation. So we have P, and then the square root and the square cubic, the cubic root, and the latency cost as well for each of these cases. So this is how they behave. At some point, one of them, the slabs, is faster, but it doesn't scale well as well. It's well known that the slabs doesn't scale well due to the limitations on the data that you have on the number of processors. So this is a table we prepared for analyzing what the network topology impact will have on the scaling of FFTs. Taking these formulas that we derive for different FFT decompositions, we can take now the network topology and analyze how our FFT will scale in each of them. So here I have presented some of the network topologies in the top 50 supercomputers. So there we can see Frontier, Summit, some others like the CPU-based, like Fugaku. And here you can see that with these formulas, we can get an idea how our FFT will scale. And for instance, for the Torus 6D, it will be an scaling as n to the power 5/18. So these kind of formulas, we have verified some of them with our experimental frameworks. And here's some of the experiments we did. Well, here in these experiments, I will present for Summit and Frontier supercomputers, which are both based on Oak Ridge. Here we have how our MPI distributions behave for different sizes. Here, the latest version of Spectrum MPI, I will use 10.4, and here is Cray and Pitch for Frontier. We can see that the Cray and Pitch behaves very well for both small and large sizes. This is the default, it's highly optimized for Frontier, but it's not the case for Summit, for instance. On Summit, we have seen that MPI Pitch, for instance, behaves better than the default Spectrum MPI for small sizes, which are very essential at large-scale FFTs. Here, I have a comparison of the different methodologies we can use to do this transposition. As I was saying, this is an all-to-all exchange, and we can do that with all-to-all, all-to-all V, or all-to-all W. So one limitation of all-to-all W is for some distributions like a Spectrum MPI, is not GPU aware, so we cannot use it with GPUs. But this is how they behave. This is for an experiment with 4 reshapes. And we have that the all-to-all V is faster for this case. And also, we have observed that at some point, not always the GPU awareness of a supercomputer is essential. But when you have a small number of nodes, it's critical to use the GPU fast interconnections that you may have in your nodes to further accelerate the scalability of the FFT. Here, for instance, I have some examples showing the pencils, slabs, and brick decomposition for different cases, like tuning on and off the GPU awareness of the network or the distribution, the MPI distribution. And this has been analyzed in several papers. What is the impact when it should behave in a better way than just moving to the host? And here is what happens at large scale. So when we have a very large scale now, what we can achieve here for 6,000 GPUs, for instance, we still observe that here is a Spectrum MPI. It doesn't handle very well, even though it has improved a lot from 10.3. The 10.4 version still behaves like this for small sizes. By a small size, I mean half a megabyte, 1 megabyte, or even smaller than that. It should behave well, but it doesn't. So I think the network congestion there and the network topology have to be some parameters for they to tune on their implementation. Yeah, and this is something we are also evaluating, like the decompositions approach, how they scale the FFTs, because many applications rely on them. And we need to ensure that this is not happening when we increase the number of GPUs. Another approach is where in Hefty we try to shrink the subcommunicator to a small number of GPUs, do the computation, and then scatter back. So that's also a powerful tool to have. And tuning this is the parameters to achieve scalability is critical. One of the experiments we performed was this one here, where we show that not always you get good scaling, like linear scaling, but you can if you tune correctly your grid, your processor grid, or your GPU grids. The number of or splitting that you use here is critical, as you can see. For some bad choices, your scaling can stop very soon. For other ones, you can scale here. This is the number of nodes that we have used on Summit. So you have a very good scalability, provided you have tuned very well your processor grids. This is critical for scaling at large number of GPUs. in this case, 6,000 GPUs. So in conclusions, at large scale, we have these still latency effects that are becoming problematic. And we also have observed the interest of many applications on doing sparse FFTs. Right now, we don't have any tools to do like a sparse communication that can take advantage of the data structure, and then with the GPU interconnects, it can give us much better results than choosing just the naive approach. The mathematical models that we can define, we can create are critical also to understanding how network topologies impact the scalability, and that has to be taken in consideration on the tuning approaches. Many libraries have auto-tuning approach, so and we must ensure that these parameters are taken care of. So another point that I show in this presentation is that you have to provide a very good choice of the processor grids for the global transposition. Otherwise, we have observed in many experiments that at some point they stop scaling. When we benchmark different libraries, we can see that many of them stop scaling, but the problem at some point was that the grids were chosen in a bad way. If you just tune your grid choice, it can still scale for many more GPUs. So, and finally, the GPU awareness of MPI distributions are essential as well. We can take advantage of them on libraries like FFT. We can tune that on and off from runtime, which is very good as well. And we need to come up with a better also handling of small messages when we scale. For instance, if we use all GPUs on Summit, we have a very small, very high number of messages of very small sizes. And what do? Like we shrink the communicator, or we just keep doing the same exchanges? That has to be also. Maybe we can add also this kind of benchmark to the OSU benchmark functionality to see what's better, to shrink to a small number of GPUs and then scatter back, or just continue decreasing the size of the messages at large scale. So that's it for me. Thank you for your attention.
Yeah, we have time for questions.
Hi, that was a very good talk. I have one question. So you said there is a need for sparse all-to-all operations, right, from the MPI side.
Yes.
Do you think neighborhood collectives can be used in those cases? Because neighborhood collectives, if my understanding is correct, lets us choose the neighbors for you. Like you can define your graphs, and currently, like MWAPITS also has good neighborhood GPU collective. So do you think that can benefit for sparse cases?
Definitely, that can help. And most importantly would be like to have the integration to the FFT itself.
Okay.
Because many applications will give you like the data already on the GPU in a certain way. And well, if I want to use MBI pitch, for instance, the collective neighbor, I have to move back to a way that you accept.
Okay.
So what we did, for instance, with Qatar, her name is Qatar, right?
Qatar. Yeah.
For one-sided communication, it was to take advantage already on the data structure and bring it to the MPI in a faster way.
Okay.
That would be amazing if we can do that now for sparse data.
Thank you.
Much complicated.
Yeah.
Any other questions from here or online?
So I guess I just want to understand what you mean by the processor grids not being like well constructed. So when you say that, are you saying that essentially certain processes are getting certain data, and then when communication happens, like there's not like good locality between where the data is and where it's going?
Exactly. If you want to do your all-to-all call, let's say, in a way that you have data, different amounts of data in many GPUs, what do? Like some people would do like a load balancing, and that is, I think most of the time is empirical. So what we see in many of the libraries that I show, they do the partition of all load balancing in an empirical way using like tools like the minimum surface approach, which is totally empirical. So we don't know which is the best. How do I balance my communication before an all-to-all exchange? So this is what I show here. We don't know exactly what's going to happen because you have many combinations of possible splitting of your intermediate grids for the transposition. So this is exponential number of possibilities. And even tuning, when we try like tools for tuning, you have so many options and you cannot tune them all. So here I'm showing the cases. If you do a bad choice of the intermediate splitting grid, you end up with a bad scaling. And yeah, if you guys can provide a better load balancing approach that has more theoretical foundation, that'd be great. But so far we don't have any for the FFT libraries. All I've seen there's empirical work only.
So like something that's like more focused on like topological aware kind of algorithms, is that like the same direction, I guess?
Exactly.
Okay, thank you.
You're welcome.
Any other questions? I have a quick question. I think in one slide you indicated like a small, medium, large. Do you see any like a common occurrences like on very large scale system? Is it small message size all we need to optimize, or medium or large? Where do you see the more applications using?
Okay. The applications that need the small size optimizations are those like I think so. Those like they need 22,000 cube or 30,000 cube FFTs. They got very small size messages, an exponential number of them. So and at the same time they require a batch of FFTs. They don't require only one. They require thousands of these FFTs because they provide many time steps, and this is the kind of application that needs the optimization for small sizes, the astronomical ones. The medium you can expect for molecular dynamic applications. You have sizes like 1 megabyte, which in our experiments, for instance, Nicole gets very good portion of the theoretical peak, but I think the new novel optimizations adding like Sharp library can even further get to that point. I think half a megabyte or quarter of a megabyte should behave very well. But when you have like a latency order messages, I think there's not much to do there. Or just you have the latency effect, maybe you can improve the network hardware for that. But when you increase, it's very hard to scale, for instance, on Fugaku. Fugaku, you have several 100,000. You can, of course, yeah. Okay, thank you again.
Okay, so let's give a thanks. Thank you.